So, today we're going to talk about Hess's law again here, and we're going to use products minus reactants, of course, and now that you guys know that pretty regularly. Before we get to the stoichiometry part here, we're going to talk a little bit about delta FH. Delta FH, of course, is heats of formation, and I think I told you guys on Friday that these are common types of questions probably that you'll see. If you know delta H, right, the enthalpy change, and you know it's products minus reactants, you could find a product or perhaps a reactant, delta FH, heat of formation, if you know delta H, because you're going to be basically doing some algebra and solving for that. So you might not know a specific reactant, but you could find it, okay? And you can use Hess's law to do that, of course, based on a balanced chemical equation. So here's our first one here. We're going to get right into examples here. Calculate delta FH. I will tell you right now that I would be surprised if you don't get one of these on your unit test, and I would be surprised if you don't get one or two on your diploma in some way, shape, or form, because these are pretty common questions. And what you'll notice here, of course, is we've given you the equation here. We're not looking for delta H because they gave it to you, okay? What you're looking for in this question is the heat of formation, in this particular case of C7H12, which I think I said last class was heptine, is what that one's called, from the following reaction of this combustion reaction here. So what we need to do is, like I said, products minus reactants, but we know delta H in this case, so we need to solve for one of those missing things there. So let's do that. So here we go. I'm just going to move it down here a bit here. So delta H here, of course, okay, is equal to the products minus the reactants. And it says here that delta H is a negative 2638.4 kilojoules. So I'll put that in there, 2638.4 kilojoules. That is the enthalpy change associated with this equation. And also, what I know is, of course, it is the products minus reactants. Well, I know the products. It is, what did I say here? 7 carbon dioxides. So let's put that in there. 7 moles of carbon dioxide. And the heat of formation of carbon dioxide, of course, from the data booklet is a negative 393.5 kilojoules per mole. And, of course, I need 6 water gases. And 6 water gases, of course, is, let's see, negative 241.5, is it? 0.8? Yeah? 0.8 kilojoules per mole. Okay? That's the products, right? The sum of the products, that's what that means in case you weren't here on Friday. Sum of the products minus the sum of the reactants. Well, on the reactant part here, I have 1 mole of my C7H, what is it, 12, yes? Is that it? Yeah, C7H12, okay? So, once again, you can notice this is pretty simple algebra now, guys. It's just solving for C7H12 here. We want to find the heat of formation for that. So, okay, let's do this. Negative 2638.4 kilojoules. And what do I get on this side here? Well, let's see here. I remember it kind of works out to be, let's see here, 6 times. Is it negative 241.8 for water? Yes? I get a negative 4205.3 kilojoules for this part here, okay? And I'm going to subtract, now don't forget this because this is important, 1 mole of C7H12. Okay? 1 mole, I don't really need brackets there, I guess, probably. That may just confuse a little bit more than anything else here. Let's see, 1 mole, oh, I just did it again. 1 mole C7H12. Okay? And if you're not happy about that, if you want to call this X, in other words, that's what you're looking for, fine, whatever, I don't care, whatever. Okay? This is old-fashioned algebra, right? So that's what you have there. The only thing with these questions is you have to be a little bit careful you know, how you're manipulating equations, because you do the wrong thing, you think you're dividing or something like that, it could go horribly wrong. I'm going to add 4205.3 to this side here, and that'll take care of that. And I'm going to move it over to here, 4205.3 kilojoules, right? And when I do that, let's see, 4205.3 minus 2638.4, I get a positive 1566.9 kilojoules, and that's for a negative 1 mole of C7H12. Yes? Don't forget there is a minus sign there. It's minus 1 mole of that. And of course, if I want to basically solve for 1 mole of that, C7H12, I divide both sides by, if I want to get this by itself, I divide by a negative 1 mole, right? And divide by a negative 1 mole here. And C7H12 turns out to be a negative 1566.9 kilojoules per mole. All right. And the heat of formation should be kilojoules per mole. Look in your data booklet, right? Look at the heats of formation there. They're all in kilojoules per mole, right? How many kilojoules is given off when you form C7H12 per mole, right? Well, it turns out it's 1566.9. Okay. Now, a couple things here with this question here is, you can look in your data booklet if you wish. Okay, but you're not going to find, in this case here, if they asked you what's the heat of formation for C7H12, you can look in here and try and find it. That's probably the first thing I would do, but you're not going to find that one in here. Because the reason you're not going to find it in here is because they want you to do all the work to solve for it, right? Now, not saying they may not give you a gimme question, but that's pretty gimme. You look it up in the data booklet. Maybe decomp would be a better one for that, looking up in here kind of thing. But they're probably not going to have that in here. And if you notice, all the stuff that they gave you here was they gave you the heat of formation. And remember, this is very, very important here. Make sure you're answering what they want, okay? Because sometimes people will say, oh, they're looking for the heat of combustion. Is this a combustion reaction? Yeah. Can you find the molar enthalpy? Can you find delta C? I know this is not really clear, guys, here, but can you find delta CH for C7H12? Pretty easily, can't you? 2638.4 divided by 1, yes? 2638.4 kilojoules per mole, yeah? Right? That's easy. That's a gimme, right? So this is quite often what students want to do because they're just like, oh, yeah, delta, whatever, kilojoules, just divide molar enthalpy. But that's not what you're asked to do. You're asked to find the delta FH, the heat of formation. That's different, okay? So make sure, do these, like, I haven't been really specific on that stuff, but one of the things we have talked about is the heats of formation. Combustion, we always do. Yeah, delta RH, sometimes we use, whatever, interchangeably or whatever. But we have to make sure we're answering the question, right? Delta formation H is a big difference than delta CH, okay? I'm not forming C7H12, I'm burning it, okay? But what is the heat of formation associated with that? So there's a lot of stuff, there's a lot of little things like that, right? And those are the little things that are going to make the big difference. Even on your test on Tuesday, you only get 25 questions. So you screw up 1, that's 4%. That's 2, that's 8%. So this could be easily, even though you think you might know how to do this might not be complicated for you, that's 4% right there. You do that 2 or 3 times, you're out of the 80, you're down to the low 80s already, okay? Or whatever it is. Well, high 80s, I guess. I don't know, I'm not a math teacher. Chemistry. All right, so anyway, moving on here, right? So you just got to make sure you pay attention to the details, guys. It's all about details here. Hess's law and stoichiometry, this is nothing new. You guys should be able to do. In fact, I'm going to get you to do the first question because you should be able to do it, okay? And if you can't, well, then you need to catch up a little bit here and make sure, okay? Obviously, Hess's law and stoichiometry, we've done stoichiometry before. A balanced chemical equation can be used to compare the amount of a chemical to the amount of energy involved in the reaction, okay? So let's look at the first one here. How much heat in kilojoules is needed to decompose 78.5 grams of sodium hydrogen carbonate based on this following equation? So go ahead and do that now. You guys can do that. I know you can. All right, so you got your balanced chemical equation here. It tells you how much heat is produced. Now remember, this is a decomposition. They're telling you that, hey, if I want to break down 2 moles of this, I need this much energy involved, right? So 2 moles of sodium hydrogen carbonate requires 129.2 kilojoules of energy to be broken down into sodium carbonate, carbon dioxide, water, gas. I don't have 2 moles of sodium hydrogen carbonate. I know I don't, because I only have 78.5 grams, and if that's the molar mass, that works out to be about 0.9344 moles. So remember, we talked about this before, guys, right? It's stoichiometry. This is, even if you don't remember this from Chem 30, this is Chem 20, right? 2 of these gives you 1 of these, 1 of these, and 1 of these, and it requires that much to do it, right? There's a direct relationship. It's a direct amount-to-amount thing, right? 2 moles requires 129.2. Well, okay, you can do a formula for this if you want. So delta H equals N delta, well, this is decomposition, right? So if you want to put a DH there, or if you want to put N delta RH, it doesn't really matter, okay? But look, how much energy is involved if I take 0.9344 moles times it by the molar enthalpy. In other words, if I'm breaking down 2, it's 129.2. If I break down 1, right, this is 129.2 kilojoules for 2 moles of sodium hydrogen carbonate, right, per mole, molar enthalpy of sodium hydrogen carbonate, which, by the way, works out to be about 64.6 kilojoules per mole. Okay? It requires 64.6 kilojoules of energy to break down 1 mole of sodium hydrogen carbonate. I don't even have a mole of sodium hydrogen carbonate. I have 0.9344 moles. Therefore, if I multiply those two, I should get a positive 60.6. No. Huh? 60.36? Yeah. Okay, all said and done. That's how much energy is going to be required. 60.4. Okay, kilojoules of energy, yes? Okay. And if that gave you a little bit of trouble, you need to start practicing some questions, because that's a straightforward one that we need to be able to do. Okay. You don't have to do it like that. I told you before. Look, good old-fashioned stoichiometry. It's a ratio proportion thing, right? 2 moles gives me 129.2. Look, you could just do this. If 2 moles requires 129.2 kilojoules, you can even put a positive there if you want. If I only had 0.9344 moles, how many kilojoules of energy is required? Cross multiply and solve. All right? You're doing the same thing. Just there's no fancy formula for it. If that's a fancy formula for you, delta H equals N delta DH or whatever. But same thing, right? 2 moles requires 129. You're trying to break down 0.9. So how many moles or how many kilojoules is required? That's it. Okay. So 60.4 would be your answer there. 60.36. I went with 3 significant digits. Probably what you'd see on your test would be 60.4 because that fits into the boxes nicely, right? 60.4. Because of course you got 4 boxes, 1 for each one of those. 6, 0, and the decimal and the 4. Okay. Good? Yes? No? Okay. Now, next, you might say, okay, let's take a look at this one. Well, let's get you guys started on this. Why don't you guys get going on this one? How much heat's released by the combustion of 50 grams of zinc sulfide based on the following reaction? Okay, yep. Yeah, just see if it's there. You want to know how much heat is released. So this is a delta H question, right? I'm looking for delta H, how much heat is released. But you're only burning 50 grams. So that's the other part of the question, right? You're not burning 2 moles probably, I'm guessing, because if you were burning 2 moles of zinc sulfide, you'd have your answer already, right? It'd be, well, Hess's law, whatever that happens to be. It's not going to be, yeah. No. All right, so I'll let you guys work on that a little bit. What's the first thing you guys need to do? First thing. What's the first thing? Huh? Can't hear you. What's the first thing you need to do? What's that? Balance it? It's balanced. What next? Find. You could find the moles, sure. What else are you going to need to do? Yeah, you could do that. You could write down the information you know, right? You could start by doing that. Sure you can. But ultimately, I need to know how much heat is released. Do you see heat up here anywhere? So you need to find it, yeah? How are you going to find it? Log Hess monster, yes? Roar. Products minus reactants. So you got the products, you got the reactants, right? Figure that out. Figure out delta H first, right? Or second, after you figure out what you need to write down here. All right, I'll let you guys work on that. All right, well, ultimately, I hate to tell you this. Just keep talking. I'm going to pause. Guys, shh. First things first, okay? If you want to calculate how much energy is involved here, look, you're burning 50 grams of zinc sulfide. Well, is that actually 2 moles? No, it's not. Okay, because if you know what, this would be a pretty quick question. It's not. Molar mass here is 97.48 grams per mole, and of course, if you divide the two, you get about. Could someone help me out here? It's a 0.5 what? 13? 12, yeah, 512 roughly. Okay, give or take a bit, and we'll come back to that in a second. But look, I'm only burning I'm only burning 0.512 moles, right? So obviously, okay, we need to figure out how much heat's associated with that. Well, I don't know how much heat is associated with that because I wasn't told. So before you can do this first if you want. I don't care what order you do this. However, at some point in time, you're going to have to figure out delta H for this equation, right? And the delta H for this equation, of course, is the products minus the reactants. And delta H, by the way, I'll save you a little. I'm going to skip a little bit here, if that's okay. Products minus the reactants. 2 times this, minus 2 times this, and you will get, as a final answer here, negative 882.6 kilojoules is what you'll come up with there for delta H. Okay? That's how much heat's associated with this particular equation. So when I say delta H is what, I say delta H is what? 882.6 kilojoules. All right? There you go. And once again, now you say, well, okay, but I'm not burning a mole. I'm not burning 2 moles. I'm burning 0.512. So that's quite a bit significantly different. Delta H in this case is delta CH. Like I said, 0.512 moles, roughly, give or take a bit. And the molar enthalpy of combustion, right? I had to figure out delta H, and I know that 2 gives me that. Well, how much does 1 give you? Well, it's 882.6 kilojoules for 2 moles of zinc sulfide, right? And if I multiply that out, or you can put in there, obviously, a negative 441.3 kilojoules would also be acceptable, kilojoules per mole of zinc sulfide that I burn. So multiplying that, let's see here. I'm going to have to go back there. Oh, is it 50 grams there? Yeah, 50 divided by 97.48. And I get 0.5129, yada. And we're going to multiply that by 882.6 and divided by 2. So all said and done, I guess I answered this already, negative 226 kilojoules. You'll probably only need 3 significant digits there, because if you go back to the question way up here, you'll only have these 3 here to worry about. okay, in the big scheme of things. Yeah. No, it comes from the question. Yeah. Okay, so that'll probably be your answer for that one there. Now, once again, they'll have a way of doing that so that you probably use, in most cases, you'll probably tend to use the 4 squares. So they might, they might give you more grams to make more moles, which would increase the energy there or something like that. So they usually try not to do that to you, but it could happen. If this does happen, by the way, since we're talking about this, remember, you got 4 boxes to fill in if this happens to be numerical response. It will say how much energy is absorbed or released. That takes care of the positive, negative part, right? Or they'll put a positive or negative part in the question. That way, takes care of both, right? Or they'll talk about just released or just absorbed, and I mean, it's combustion. You should be getting heat out of it. If you're not, that's bad, okay? So they'll probably just say how much energy is released, or they'll say that, actually, I think they said that in the question, did they not? How much heat is released, so you know, right? If you did run into this problem, you'd have to do 2, 2, 6 like so, and you'll leave the 4th one blank, yes? Always left to right like a book. It tells you that in the beginning too, okay, on the test. All right, moving on. That good? Questions, anyone? Yes, no? Oh, now we got a little more review stuff here. Oh, we like review, eh? See, this test that we're reviewing every day, everyone's like, are you going to review at the end? The answer is no. You're going to review at the end. But we're reviewing every day here. This is awesome. A bomb calorimeter. Oh, balmy. Okay? Look, right there. There's another key. If you don't know bomb, you know kilojoules per degree Celsius. That's big C, right? So we know it's big C already. All right. Calculate delta T. 3.7 gram. This is methanol. That's okay. You don't need to know that yet. You'll learn that in Unit 3. CH3OA is burned in the calorimeter. Well, let's see. Let's talk about what's going on here. We got energy that's lost in this case, negative. We got energy that's gained, right? You're talking about how much heat is going up, etc., etc. We're talking about a bomb calorimeter here. So big C delta T. When you see kilojoules per degree Celsius and you see delta T in that part of that question, you're thinking, hey, that's C delta T. Where do I use those types of questions? Probably this kind of thing. That's gaining energy. What's giving it the energy? Well, in this case, it's the CH3OH. It's the methanol. Is that what that's called here? And of course, we know that that's probably N delta CH over on this side here. Okay. How many moles of methanol am I burning? What's the molar enthalpy of methanol? How many kilojoules do I get for every mole of methanol? How much heat do I get from burning a mole of methanol? Well, let's see. Let's start putting in some numbers here. You know, guys, once again, I expect you guys to come up with that part. I'd expect you guys to start putting some numbers in. Don't tell me I don't know what to do. Okay? Put some numbers in. See what happens. You never know. 4.18 kilojoules per degree Celsius. That goes right there. 4.18 kilojoules per degree Celsius goes right there. Calculate delta T, it says. So that's what I'm looking for. I'm not going to know that right now. N. Well, gee, can I find N here? What do we got? 3.75 grams of methanol. I can do that. Look, I can put in this at least. Methanol, right? Methanol CH3OH, so that's what? 4 hydrogens, an oxygen, and a carbon, and you get what? 32.05 grams per mole. Okay, good. Now let's put in delta CH here. Molar enthalpy of combustion, right? What's giving me the heat? Well, it's burning methanol, 3.75 grams of it. So that's going to give me the heat. Where does that heat go? It goes to the bomb calorimeter, which is the C and the delta T. Do I know delta CH? Does it say so in the question? Nope, only got these 2 numbers here. No, but I know I'm burning it, okay? So I don't have delta CH. Well, you can find it, right? Combustion of methanol. Now, some of you guys are going to be tempted to look this up in the data booklet for delta FH. We're not forming methanol. That's not what's being transferred to the bomb calorimeter. We're burning it. So we need to have a burning question. Huh. I don't know if that makes sense, but I thought it was kind of funny. plus oxygen gives me carbon dioxide and water. But it's in a bomb calorimeter, so it has to be a liquid water, yes? Okay, that's where this stuff comes into play here. So I did this last class here, but basically if you try to balance this right now, it's not going to work out. You got one carbon, you got 4 hydrogens, so I could put a 2 there, but then I got even oxygens, and I'm going to have an odd oxygen here. So basically I'm going to go to here, I'm going to put a 2 there. Let's see, I need 4 there. That's 4 and 4 is 8 oxygens. I got 2 here, so that's 3 there. Okay, should be the right balancing for that. Old Loch Ness Monster will give me delta H for this, because I don't know what delta H is, right? I actually do. I'll tell you this. I'll give you a hint. It's negative, because it's exothermic. I'll even put that in there, because that's the kind of guy I am. Okay? All right? So you need to find delta H, right? Products minus reactants. So delta H, sum of the products minus the sum of the reactants. Okay? What is delta H for this particular burning of methanol? Well, let's see here. 2 carbon dioxides. I'm just going to skip right to it, guys. Let's see here. 2 times 393.5. Oops. No, that's wrong. Negative 393.5. And 4 times water gas, which is a negative 285.8. 285.8 for that one. Okay? Negative 285.8 because it's a liquid. Okay? 285.8 for that one. Minus 2 times methanol, which is a negative, and you got to be careful with this, 239.2. Make sure you pick the right one. There's methanol and there's methanal. Those are different, okay? Methanol. And you should get, all said and done here, a negative 1451.8. Yes? Somebody else? Negative 1451.8? Yes? Okay. Kilojoules for that. Is that right? Somebody else get that? Or did I mess that up? I got the minus there. I think it should be good. Yeah, should be good. All right. So negative 1451.8, all said and done. And don't forget, by the way, sorry, this is 0, right? Any element is 0, so I didn't include that. You can, obviously, 3 times 0, so 0, if you really want to, but, right? Okay, good, yes? So now we know delta H up here, right? So if you go back up to our equation here, well, we don't have our equation, I guess it's right here, I would say negative 1451.8 kilojoules is how much I get from this particular equation. So this would be my balanced thermochemical equation right there, right? Burning 2 moles of methanol gives me 1451.8 kilojoules. Okay? How much am I actually burning? Am I burning 2 moles? I doubt it. Looks like to me 3.75 grams out of 32.05. That's about a tenth of a mole, yeah? So like 0.1 of a mole, roughly. So that's how much I'm burning, right? What's going to go in here? Delta CH. How many kilojoules of energy do I get per mole of methanol? Well, it'd be your negative 1451.8 kilojoules divided by, and I burn 2 moles will give me that, so 2 moles, right? And that's my molar enthalpy, kilojoules per mole, which, by the way, works out to be about 725.9 kilojoules per mole, okay? So, or you could just do that and put in 725.9 kilojoules per mole, okay? Yes? Okay. Good so far? Questions, anyone? Do I have any wrong numbers there that you don't believe me of? Okay. So, you need to solve for delta T. That's the question, right? That's the only thing left to solve for, by the way, in case you haven't figured that out. So, let's do this. Let's see. I got that, and I'm going to have to take, what is it, 3.75, so I'm going to multiply 3.75 divided by, sure, 32.05. So I got that. I get about 84.9 on this side kilojoules, right, is given off. It takes in 84.9 here because energy lost has to equal the energy gained. And I got a 4.18 there, so I'm going to divide both sides by 4.18. And all said and done here should be delta T here should be 20.3 degrees Celsius. And it is a positive because, look, negative here, those two will cancel. So it's a positive 20.3 degrees Celsius, which makes sense. You would expect the temperature change to go up. It's exothermic, guys. So if you're giving off heat, it's going to be absorbed. The temperature should go up, right? 20.3 degrees Celsius. Is that good? Did I mess up any of the numbers, though? I thought last class maybe it was 20.4. Is it? Depends on what number, I guess, we used. Maybe I messed up on one of these. Anyway, it should be all good, but unless I messed up typing one of these numbers in, I don't know. Is 1451.8, did you guys get that? Yeah? Well, it should be okay then, I guess, if that's the case. Okay. Sometimes I know the numbers, but they don't correspond to the calculator for some reason. All right, good. That one's a lot more involved. There's a lot of stuff that goes with that, right? There's a lot of work there for that one question. You're probably not going to get that for a diploma question because look how long that took us, right? It took us a while. But there'll be something to do with that in some way, shape, or form. So how are they going to save time? They might give you this. So they might give you that. They might give you parts of it or split it up into a couple different questions. So they might stretch it over 2 questions kind of thing. Or something along that line, okay? But they'll definitely, they'll obviously have stoichiometry and Hess's law, something to do with that in this particular example here, okay? They have to. It's a big part of it, right? So, like I said, that's a little bit of practice with everything, right? And like I said, they may not ask that entire question, but they'd ask some portion of it. All right, good? All right, I think we got one more here. Yep. Right, yeah. Okay, this one here. Sample of octane is burned completely in an open system. The reason they say it's an open system is they're trying to get you away from the bomb calorimeter. They actually give you the equation in this one. You'll notice here that it's not in the bomb calorimeter because water is a gas. So they're just saying it's just basically burned, okay? Calculate the mass in grams of octane that has to be burned to heat up 10 kilograms of water from 20 to 95. So they're saying that they're burning octane. And then when they burn this octane, it's heating up the water, okay? So you have to think about it in terms of what's going on here. You're burning some octane, and where's that energy going? It is going to water. So you're burning the octane, and you are gaining the temperature or that energy by water. And we know that if we want to gain the energy by water, usually when we talk about that stuff, we talk about MC delta T, right? Sure. And we talk about on this side, well, gee, if we're going to burn octane, how many moles are we burning? And how many kilojoules per mole do we get from burning octane? This side, we're going to say right here, by the way, is we know it's 10 kilograms. If you look back up the question, 10 kilograms of water. We know it takes 4.19 joules per gram degrees Celsius to heat that up. And we know that the temperature change was, what was it, 95 to 20, calculator 75, yeah? 75. Final minus initial, don't forget, okay? So 25 to 90, or whatever it was, 20 to 95, I guess, 75. On this side here, we need to talk about, okay, N and delta CH. Turns out, I don't know N for this question. If you look back up here, there's no mention of how many grams we burn. There's no N. And there's no delta CH either for this. That's all we're given so far. But once again, I would expect, when I check homework, guys, you should have at least that. Okay? That's just putting in stuff you know. Right? I mean, that's what we should be able to do. We should know what all these things stand for. Now, of course, we need to figure out what's the molar enthalpy of combustion. We can figure that out. We got Hess's law stuff now we can do, right? Anytime you see this kind of equation here, guys, I'm going to tell you right now. Look, when we talk about Chem 30, right from day one, we said there's always heats associated with chemical equations. That's all we've been talking about this unit. Well, there's Chem 20 right there. How we're going to make a Chem 30 and apply to us, we need the delta H thing, right? I mean, that's all we've been talking about here. So we need to figure out what is delta H, right? That's what makes it Chem 30. So, once again, products minus reactants, Hess law, right? All that stuff. So, down here somewhere I'll do delta H equals products, some of the products, some of the reactants, right? Let's see here. I'll try and do this on my calculator here. 16 times negative 393.5, and we got 18 times a negative 241.8. And we're going to subtract from that 2 times my octane, which is octane 250.1, negative 250.1. And we type all that in, and we get a negative 10,148.2 kilojoules. Okay? So right here, at the end here, I'd say delta H is negative 10,148.2 kilojoules. Okay? Negative 10,148.2 kilojoules for that particular equation. And that's, of course, when you burn 2 moles of octane for that. Well, let's see here then. I guess I can go down here and say negative 10,148.2 kilojoules for 2 moles of octane, which, by the way, if you're not happy about that, is 5,074.1 kilojoules per mole, right? So right here you could say 574.1 kilojoules per mole of octane. Well, let's see. You got the mass CT, delta T. You got delta CH now from enthalpy change. I could figure out N. Okay. So we take 10 times 4.19 times 75 divided by our 5074.1. Oops. And once again, by the way, negative here cancels. So N works out to be 0.619, which is probably a good thing that they cancel, because otherwise we'd end up with negative 0.619 moles, and that's probably pretty much impossible, I would think. Can't have negative moles. So we got N. We got the molar mass of octane, or we could find it out anyway. What is it? 8 carbons and 18 hydrogens. Yes. 114.26 grams per mole. And the question was, what's the mass that I would need to burn in order for that to happen, right? So the mass I have to use here is times 0.61932.165, 70.8, oh, no, well, 70.8 kilojoules, right, rounded. Actually, all said and done, probably 71 gram, sorry, gram, not gram, 70.8 grams, 71 grams, sorry. You got moles and grams per mole, your answer would be grams. 71 grams all said and done, because there's only 2 significant digits if you go back and look at the question there for the temperatures and stuff. So there's only 20 to 95, okay? There's 10 there, so 2 probably, 71 probably would be your answer for that one, okay? All right, any questions for that one? Now, once again, that's a lot of work, and I get that, but it's kind of a, we're trying to review with you guys too as we go through these questions, right? Energy loss, energy gain, that kind of stuff, MC delta T, all that good stuff. But remember, you have to find delta H, Hess's law, and then you know, figure out the molar enthalpy of combustion. And once again, you know, I can't stress this enough. It's not talking about, this is not delta FH, okay? Yes, you use delta FH to figure out delta C, delta H and then delta CH. But we're not getting the energy from forming octane. We're getting the energy from burning it. Very different things, right? Formation reactions, combustion reactions are very, very different. So we have to keep that in mind when we're doing these questions. What are they actually asking me, right? So we need to decipher that and make sure we understand that, right? So products minus reactants, Hess's law, that gives you delta H. And then you can figure out the molar enthalpy of any one of those things. You don't have to just focus on octane. You could do oxygen even if you wanted to. Okay, you do 16 carbon dioxides or 18 waters. You can calculate the molar enthalpy of any one of those and figure out stoichiometry stuff based on any one of those, right? If I made 50 grams of carbon dioxide gas, how much heat did I also get from this equation? That could be a question. Well, now your 50 grams is over here. Molar mass, figure out N. Well, gee, 16 moles gives me 10,148.2 kilojoules. If I had 50 grams here made, how many moles is that? How many kilojoules do I get from that, right? Yep. What's what now, sorry? Delta H of H2O. Water's over there at the bottom. Yeah. Water. W at the bottom. Is that what you're asking? Yeah. All right.